This is C. So like that, if I give C to the power of 5 and not get those many, total 6 qubits are required. Out of that, 5 are known as control bits and 1 is target bit. So target bit will be flipped. Okay. Now we'll see 2 qubit C naught gate. Now we'll see what is the unitary matrix for this. Oh, sorry. How to write the unitary matrix? Okay, C naught of at 0 0, C naught of at 0 1, C naught of at 1 0, and C naught of at 1 1. Okay, you write the result of each of this, then that is going to be the final answer. I think all of you can write it now. The final unitary matrix to represent that C naught, because we have seen the symbol. The symbol for C naught gate is like this. And as I already told you, each gate in the whole quantum environment is one unitary matrix. As we already discussed in the morning, unitary matrix is nothing but U multiplied with U dagger is going to be I. What is the U dagger? Complex conjugate of U. What is complex conjugate? Transpose of the given matrix and making plus I to minus I and minus I to plus I in the complex number, that is known as complex conjugate. It's very simple definition. You see that. So each one is one unitary matrix. Okay. You see it afterwards. Otherwise, it is nothing but one matrix. Now, how to get that matrix? I don't know. You need to write the result of each of the valid combinations in this matrix. The result. What is Cn of 0 0? Here you are already written now. 0 0. Now you convert this into column vector. How to write column vector for 0 0? 1 0 0. Very good. Then what is the Cn of control naught of 0 1? 0 1 only. What is the column representation? Column vector representation of 0 1? 0 1 0 0. Okay. What about Cn of 1 0? 1 1. So what is the column representation of 1 1? 0 0 0 0 1. Similarly, what is the representation of this one? Because it is 1 0. How do you represent 1 0? That is ket 1 0 actually. It is known as ket 1 0. How do you represent ket 1 0 in column vector? 0 0 1 0. Very good. That's all. This is known as unitary matrix for C naught. So can you give unitary matrix for CC naught? 3 qubit. Give unitary matrix for CC naught gate. Previously you already written the result here. Just you need to write the respective result which are known as the ket representations into the column vectors. Each column vector need to be written here to get the matrix. Now what is the size of this one? 4 by 4. Can you tell me what could be the result for CC naught gate? 8 by 8. Okay, you write 8 by 8 matrix for CC naught. Yeah, how to get the matrix? CCN of 0 0 cat 0 0 0, then CCN of 0 0 1, and please start using this notation, cat notation, so that after writing some 20, 30, 40 times, you will be familiar. Otherwise, initially you will be in confusion how to write this, where to put, what is that. But you start practicing it from now onwards. Then you know what is the result of this one. Is it the one? Is it correct? No. One should be written here. Okay, what about 2? 2, there is no change. 3 also no change. 4 no change. 5 also no change. 6. Okay, now what is CCN of this 110? So it became 111. So 111, how do you represent 111 in column form? Last one. Whereas for this one, this. That's all. Now can you give unitary matrix for 3C is not, C cube not, C power 4. Now is there any great maths which you never know? All simple maths, only getting matrix. After that we need to multiply them, then you will get the result. That is known as result of the whole circuit. So whenever I say I am using circuit, so 3 qubits. So this is the meaning of this. Can you tell me what is the result now? When I give all zeros, what is the output I am getting here? And just now I am writing in the circuit form. I have written it like this: 0 1 0. 0 1 0 only. This is not the result of applying what is that CC not gate on this particular input. But here this matrix will give the output for any of the 8 combinations. It will work like for any combinations. Here we have written it for 1. So like that, if you write it for individually, it is okay. Otherwise, actually to get all the combinations, we need to apply something known as Hadamard gate. Then you will get the output of each and everything as a single expression. Then we apply measurement. That we'll see in the coming classes. At least up to this, I hope all of you understood, no? That's all. So you can go with like this n number of what is that gates. Now we'll go back and see the Hadamard gate. Whether you understand it or not, simply you by heart it now. Okay, please note down this. This is the Hadamard gate is the most powerful to understand the concept of the superposition. Superposition. It will convert that 0 and 1 into its respective superpositions. So this is the meaning of it. Now from this, please can you give me the final matrix, unitary matrix? Same procedure, whatever the procedure that we followed for single qubit, you follow it and you give me the final unitary matrix for Hadamard gate. So the same thing I have written previously for poly X gate. X of 0, I have written X of 1, I have written what I have written X of 0, 1, and this is 0. From this, you have given me like what is that? 0, 1, 1, 0. This is known as the result of what is that? Poly X gate. Finally, you need to give me some matrix like this from these two expressions. Yeah, please, you do it. Simple maths, school mathematics. Actually, how did you get this? By writing the result in this one, no? What is that? X of cat 0, X of cat 1. Now here also same thing. How to get the result? H of cat 0 is going to give you one column and H of cat 1 gives you another column. Then you write and give me that. What is H of 0? Okay, you do the simplification and you give me all different forms of it. Finally, you need to give me one 2 by 2 matrix. Please, all of you try. Completed? Yeah, please come. And seriously, come here. Very good. So you write it here, whatever that you get. The result has to be one 2 by 2 matrix. Okay, very good. Can you take 1 by root 2 as common and write? Yeah. So, can you explain how did you get this? Yeah, to your audience. You want a mic? I'll give mic. Hold it and explain, no issue. Yeah.
And my take this one is equal to this. There, we expand this and this. So get on 0, writing column matrix as 1, 0. Plus, get off 1 as column matrix 0, 1, 1 by 2. Equating this to 1 by root 2. And 0 plus 0, 1 by 2. This is element of 0.
Yeah, please, all of you understood this?
And same element of 1 is same. 1 by root 2.
Yeah, okay. Continue.
Minus
Yeah, good. So first she simplified that into this form. Finally, she has written this here and this another one here. Then this is the final result. But if I want, as I asked her to further simplify, 1 by 2 has taken common and 1, 1, 1 minus 1 is written here. That's all. So it looks like no, that same maths revolving there only. So just you need to spend just 1-2 minutes time just to how to get this 2 by 2 matrix. Because the target is to get 2 by 2 matrix. Okay, great, very good. Nice job. Thank you. Good. Yeah, please claps, claps. Ah. No, that's why I'm insisting. No, don't look this as a entirely great or new subject. It is very, very, very simple. 9th class, 10th class mathematics. That too only 2 topics. And in addition to your any matrix multiplication, I think you are aware of matrix multiplication a lot. We need not discuss, but only that. But of course, so far there is nothing that we touched about complex numbers or you not even vectors. It is normal. The only thing is that you know not operation, and we extended it. Yeah. So I think now with these 3 gates knowledge, now we'll see something what we have done in our image processing. So like that you can go with n number of gates like this. But once again I'm telling you, Hadamard gate is very, very crucial. Just that will create our actually what is it superposition state in our entire quantum environment. And once again I'm telling every gate is one unitary matrix. Now, when I say that I am applying gates, with a single one you have seen, no? For example, if I say Hadamard gate, can you tell me the result? What is the result that I need to write here? I have written, no, these things you need to remember. 1 by root 2 ket 0 plus 1 by root 2 ket 1. Similarly, when by chance if it is 1, then this becomes minus. But in the formula, he has given it for general. When it is alpha, then you need to multiply, that means alpha, sorry, when it is psi, what is psi? Alpha ket 0 plus beta ket 1. When you apply it on this, that means you need to apply that unitary matrix on this one, finally you will get the result, which is works for anything. It is simple multiplication. I'll show you that. This is one, and by chance if I say that I want to make one circuit, obviously circuit is made with quantum gates. I'll say I applied Hadamard gate, then some X gate, then X gate here, then Hadamard gate. Okay, right. Now I have given 0 and 1. Can you give me the result? Please all of you give the result of this one. Apply Hadamard gate on 0, and for that result you apply X gate and give the result. Of course, I am calling this as one circuit, but there is no link between these two. But when I apply NOT gate, C NOT gate like that, we can combine these two. But as of now, I applied individually the Hadamard gate on ket 0. Yeah, please you tell me the result here, and we'll see how to get the same result by using matrix multiplication. Yeah, previously you have written them individually. Now I ask them to write it in sequence form. First you apply Hadamard gate. For that you apply X gate. When you apply Hadamard gate on 0, what you will get? 1 by root 2 ket 0 plus 1 by root 2 ket 1. Now you apply x on this one. Then it will become 1 by root 2 ket 1 plus 1 by root 2 ket 0. Okay, right. Now same thing is equivalent to matrix multiplication. So which gate is applied first? Hadamard gate. So you should write Hadamard of 0. Then after that you applied X gate. Then you write the equivalent matrices for all of them. What is the matrix for X gate? Unitary matrix for X gate. Unitary matrix for X gate you already written, no? 1 0 0 1. Is it correct? This is not correct. What is the unitary matrix after applying X gate? 0 1 1 0. What about Hadamard gate on 0? Only on 0 now. Okay, no, sorry. You give Hadamard gate on everything. What is that? 1 1 1 minus 1 multiplied with this 0 means. Okay, first you do the matrix multiplication for these two. Do the matrix multiplication for this 1 by root 2. No, this is 1 by root 2. Yeah, what is the matrix multiplication of this? Normal matrix multiplication. First row, first column, first row, second column, then summation, all that. So 0 1 0 1 1 1. No. 0 into 1 plus 1 into 1. 1. 0 into 1 plus 1 into minus 1. This is minus 1. What about this? 1. What about this? 1. And preceded with 1 by root 2. Then you multiply this with 0. What is that? Vector representation of 0? 1 0. You do matrix multiplication and tell me. This is 2 by 2. This is 2 by 1. What is result? 2 by 1. Okay, what you will get here? 1 into 1 and here 1 into 1. So now if you separate it, now 1 1 you write as ket 0 ket 1. How do you write that? Can I write 1 1 as 1 by root 2 into 1 0 plus 1 by root 2 0 1 1 0. Can I write it like this? Whether I get the same result or not? Then this is nothing but what? 1 by root 2 into ket 0. No, ket 1, no. Ket 1, this is 1 by root 2 ket 0. Is that same result I got there? 1 by root 2 ket 0 and 1 by root 2 ket 1. 1 by root 2 ket 1 plus 1 by root 2 ket 0. See, this is crucial important. So 1 1 can be written as 1 0 plus 0 1. This is the point that you need to understand. The column vector 1 1 can be written as 1 0 plus 0 1. So when I say 1 0, this is nothing but ket 0. When I say 0 1, this is nothing but ket 1. So the whole the output of this circuit is once again can be represented as a matrix. So if I start from here, can I come to this one or not? Multiplication of these unitary matrices. So once again I am telling gate is nothing but unitary matrix. Once if you know the unitary matrix, the result of this applying any circuit is nothing but multiplication of these unitary matrices. So even if you start working with this, generally people say that the entire unitary matrix result can be the entire result of this matrix, this circuit can be obtained by making one unitary matrix. See, nothing. If I multiply these two matrices, whether I get matrix or not. Okay, so combining all of them is also finally one unitary matrix. for what is that? Gate, you will have equivalent unitary matrix. For the circuit also, you can obtain the equivalent unitary matrix. So this is the whole theme of your entire quantum computing logarithmically. If I say the Deutsch algorithm, so they will be making one circuit and finally they will represent the result by using one unitary matrix. Either writing the whole circuit, or if you are able to get that final unitary matrix which is made with all these gates, is known as the result of that particular what is that the program for that particular algorithm. Similarly, for anything, even not only image, so far we did around 6 to 7 basic algorithms, and we started working on image processing related to this. Everywhere it is all about making the circuit. Making the circuit is nothing but usage of gates. Usage of gate is nothing but usage of qubits. So once if you say that you are using you are using gate, for each and every gate you will be having equivalent unitary matrix. Okay, and but the very important thing that you need to remember here is that whenever you are working with multiple gates, okay, don't multiply h into x. Don't do it in this order. It is very basic. Okay, yeah. Now this is your ket. Which one, for which gate is applied on? Now I am writing alpha here. Now you tell me which one is correct out of these two. Sorry, I will write it clearly. You write these two and mark one of them as wrong. For example, this is ket psi and Hadamard gate and Oli-X gate and Rx theta. Okay, you don't know this, but let us assume that we applied a rotation X gate. Then I am writing one expression, you tell me which one is correct. H into X into Rx of theta of ket psi or Rx of theta X into H of ket psi. So when I am using the unitary matrix for each of them, which order is correct? See here, this is input and these are the gates applied in this order. Now which expression is correct? This one is correct, this one is wrong. Because see, what is the first operation applied? Hadamard gate. So this is the first one. Second, X gate. Then third. This is the correct order. So you have to be very cautious in the beginning. After doing it some 2-3 examples by yourself, then you will feel like comfortable with all this. Okay. Okay, then last thing. Can you tell me what is Hadamard on? Okay, I think it will take some time. I'll show you directly the one which we have done related to image processing. At least all of you felt a little bit comfortness with the gate and circuit. Okay, right. Then Okay, I'll show you how to obtain the negative of the photograph. Which one is on, off? Off or down, no? This side. Which one is off? I think image negative, have you ever seen negative of the photograph? I think these days you are not seeing, but in nowadays, no, we used to take the photograph by using reels. When we go to that dark room, they used to give reels first, then they develop it. Now we need to see how to get the negative of the photograph. First of all, you listen here. Actually, I am in image processing from last 25 years or so. But only one thing I can tell about the whole image processing is, you remember, if you understand this, everything you can do it by yourself. Inside the computer, a photograph is nothing but a two-dimensional array. Okay. Yes, here. Actually, this is one photograph. When you open that photograph by using any of the image processing supporting software, you will be seeing that as an array with some numbers 2, 3, 4, 5, 7, 2, like that, based on the size. Only one statement about image processing you can start learning by yourself. Now, if I ask to do something which is known as processing of it, doing something to these numbers and getting one more array is all about image processing or photo processing or picture processing. For example, let us assume that I have given you one photograph and assume that there is some red color in that. Okay, just assume that I have given you this photograph and assume that there is some red color in that. I have given a hard copy to everyone. Then I ask you to make red color to blue color. How will you do that? Even in place of you, even I keep second class, first class student, same work I have given. Then how they will do it? If you feel this is big question, you tell their answer. I have given photo and there is some yellow color in some location. I ask them to make yellow to blue color. How they will do that? No, not image processing, normal photo, printed photo. And I have given all the sketch pens to them. They will take blue sketch pen and they will identify yellow color. No, they know at the age of second class, third class, they know at least minimum colors. Not like our madams, because they, how many yellow colors you know, madam? 55 yellow colors you know. No. Mostly whenever you go for shopping, no, because in Vijayawada, whenever I go with my sister, because there are almost 100 yellows, but they say that no, this is not matching, this is not matching, this is not matching, or are very close to each other. But of course, that much level is not required at the age. Just converting blue color to or yellow color to blue color. Directly he will take one blue sketch pen, and he knows that yellow color. Simply he modifies it. So that is known as photo processing. I have given him one photo, he processed it and he has shown me that photograph. Then image, that is also known as image processing. That also can be considered as picture processing. Now we need to do the same thing with the help of the computer. Now in the computer, I am telling that 2 means yellow and 10 means blue color. Now how will you write a program? See, once again I am telling, that is manual. You made it, but when you opened it, I am telling that this is nothing but an array, and I am telling no, 2 means yellow, 10 means blue. I ask you to write a program to convert that yellow color to blue color. How will you do that? Replacing in the original photo, initially you will be copying that same photograph here, and you are replacing 2 with 10. Then displaying the photo. Then here what you have done actually as a programmer, just I have given you one array and you replace some of the numbers in that array with some other numbers. Now really I am telling you, no, The whole image processing is all about that. Somebody is giving us an array, doing something to those numbers and getting one more number. Oh, sorry, doing something to those numbers and getting one more array is all about image processing. So whether you call it as satellite image processing, medical image processing, or any image processing that you consider, how much big terms they use or you use, for a programmer, it is nothing but doing something to the given array. So that's why even I believe that a 10th class student who knows basic programming of writing loops and if conditions, he also perfectly fit into working with image processing. You don't require BTech, MTech, and from here and there. Because basically you need to understand that how big the algorithm may be, how complicated it may be. The whole image processing is this, working with the numbers in the given array. Okay, now as I told, this is a given image. Obviously, this is an array. Can you guess how I am getting it? And here I am telling that this numbers contains, okay, 255, 0, 4, 21, and so on, 0, 255. Then what they are doing is that they are subtracting all the values from 255. That's all. Now, if you subtract all the values of this array from 255, what you will get here? 0. Here 255. Here 251. Here 220. 255 minus 21. 234. So like this we get. And one more thing you remember, 255 is used to represent the brightest value and 0 is for the darkest. So this is how the negative can be obtained. Now is it a great program? Only one line code actually. How do you write a code for this? Simple. For loop, two for loops, and B of ij equal to A of ij, 255 minus A of ij. Only one line code. Then with this, you will get it. Now, this is known as classical. I think morning I have shown you one diagram, no? So getting the result by using classical computer, you are getting it. But now same thing we need to get it by using quantum environment. Now I'll show you how we can get the same result by using quantum environment. So obviously what I told, we need to make the circuit. So this is the circuit we made. And to make this circuit, see, this is the array. Can you tell me what is the result I should get for this array? Negative. After applying negative, assuming that 15 is the maximum possible value, I need to subtract all the values from 15. And what is the result I am expecting? I have to get 15, 10, 5 and 0. Okay. Now, as this is the classical data, I need to convert that into quantum representation. That means I need to finalize how many qubits are required to do this whole process. So first we need to decide how many qubits are required to store the positions. Actually, how many values are there total? 4. 4 values. If you convert that, if you take, this is easiest method I am telling. So how many bits are required to represent 0 to 3? 2 bits. Okay, in same way, I am taking 2 qubits. 2 okay, 2 qubits I have taken to represent the position. Now, how many bits? No, forget about qubit. Normal bit representation only. How many bits are required to represent 0 to 15? 4. So that's why I have taken 4 lines, which are known as 4 qubits, represents the gray value. Okay. So the initial circuit is going to be like this. So please all of you start noting down this diagram in your notebook. So initially you have to take 6 horizontal lines. Each horizontal line is known as qubit. Why 6? 4 for values and 2 for positions. And by default, everything is considered as at 0, the default value. Like in our Dev C++, if I give int a and if I print a value, what is the value I'll get? 0. By default it is 0. But in some compilers by default it is garbage value, but here it is 0. So this is the first initial configuration. I have taken total, and here I have given the names to them as Q0, Q1, Q2, Q3, Q4, Q5, and where Q0 is the LSB. So please, I have written it like this: Q0, Q1, Q2, Q3, Q4, Q5. Where this is LSB and this is MSB. Up to this, have you understood? Okay, now I am applying hard gate on both of them. So now please all of us here. When apply hard gate on, okay, if I don't have this, what is the result? Okay, what is the total result of this one? Only 6 zeros. Okay, there is no gate applied. Initially, as 0, 0, 0 input, there is no gate, we are getting 0, 0, 0 as output. Now, second step, please you write it. This is step 2. Apply hard gate on Q0 and Q1. Apply hard gate on Q0 and Q1. So by applying that hard gate on Q0 and Q1, the final result is going to be like this. So this 0, 0 will be made into 0, 0, 1, 1, 0, 1, 1. Because as I told you, hard gate will get your superposition. By applying hard gate on 0, 0 will result into the result of this entire circuit is going to be with these 4 numbers. What is that? 0, 0, 0, 0, 0, comma 0, 1. This is 1, 0 and 0, 0, 0, 0, 1, 1. But instead of writing it like this, I am writing it in this form. This is for our convenience, because we know there is a matrix and we need to get in that form. That's why I have written it. Otherwise, 1, 0. This is the result after applying step 2. Okay, now in separate page you write, if I apply hard gate on these 3, can you write the result? Please all of you write it. Just you leave like one page there and you write. You take 3 lines and apply 3 hard gate on those 3 lines and tell me the result of this whole circuit. The status of the whole circuit, not result, the status of the whole circuit. What you can expect here? Is there any change in these 3 values? No. So when you apply hard gate on these 3, the simple meaning is that it is going to give you all the combinations of with 3 bits. Then what are all that you will get here? 0, 0, 0. So there is no change here for Q3, Q4, Q5, no change. Whereas for Q0, Q1, Q2, what you will get? All the combinations 0, 0, 0, 0, 0, 1, 2, then 3, 4, 5, 6, 7, 8. So in some textbooks, instead of writing hard gate like this, they use like this also. Both are same. Applying hard gate individually or saying that combinedly applied on these 3, they are exactly same. I am telling you, this is the basis for almost all the algorithms, hard gate. And in a simple way, whether you understand it or not, I think is there any difficulty in telling this? When I apply hard gate on these 2, you will get all the combinations of that. When you apply hard gate on those 3, you will get, if I apply hard gate on these 4, you will get the result accordingly. Okay. So now,
hello. No, this
yeah,
is
now
this is Euronics. Yes. हाँ बोलिए.
बोलेगा उन्होंने. Yeah. Now.
आप sorry मैं तो ये बॉम्बे में हूँ. आप बंगाली में बोल रहे शायद
Hello. Hello. Hello.
Do you have 1 1 here? No. Do you have 1 1 here? No. So that's why initially this one got changed. Now after that I applied one more CC naught. What is this CC naught now? Q naught and Q1 and Q4. Now will it be flipped? Will it be flipped to 1? No, because these two are not 1 1. What about this one? Yes, this one will be flipped. Then will it be flipped? No. This one? No. Now you see here, by doing it, so now what is the value of this one? Previously we had 0 0 0. Now we made that into 0 1 0 1. What is the decimal equivalent of 0 1 0 1? 5. Because first our target is to make, what is the original value? 0 5 10 15. So our target is to make 5 in the second location. Yes, we got 5 here. Then what is our next target? To get 10 here and to get 15 here. But logic is same. First you make sure that you are making these two as ones. Now in this situation, you tell me after this, how to make 0 0 as 1 1? Apply NOT gate on both of them. Now that is the second result. Next result, you see here. I am applying 2 NOT gates so that these two will become 1, whereas in the all other locations you won't be having 1 1. Then simply apply CC naught, because our target is to make 4 zeros as 1 0 1 0. So how to make this as 1? Apply some CC naught gate between these two as control bits, and this is target bit. So because of that, only this one will get affected, and now because of this one will get affected. Now as of now I got 0 here, 5 here, 10 here, and still it is 0 0. Now can you tell me what is the next step? How to get 15 here? Now this is the present situation. Here 0 1 0 0 1 1 and 1 0. Yeah, please, all of you easily you can tell, those who have followed up to this. How to make this as 1 1 first? There already 1 is there. How to make that 0 as 1? Apply one NOT gate. Okay, applied one NOT gate. Then this became 1. As there are 4 zeros, I am applying 4 CC not gates. So by doing it so, we got the result. So now the same thing can be implemented by using this IBM environment. The circuitry is drawn. Then to get the final result, we need to apply NOT gates. When I apply NOT gates on this one, now what happened here? 0 became 15, and this is 10, this is 5, and this is 0. So that is how we made 0, 5, 10, 15 as 15, 5, 15, 10, 5, 0. That's all. For that, we have written the program in Python. For that, we use Qiskit library. Please all of you remember, by importing that and by using some little bit of some technical terms and syntax, you can do that whole process. But I think all of you followed this very simple operation. Then we applied that same program on this Lena image color, and this is for color image. And so it's like that you can explore a number of things, and even you can explore quantum machine learning, quantum deep learning, quantum watermarking. So like that, almost everywhere people are talking about this quantum, and they are trying their level best to incorporate. As I basically work in image processing, most of the time I like to combine image processing with quantum. So almost we achieved 10% of whatever we are thought of doing. But even there are around 20 internship students with me now. We are all exploring that. Mostly in next 1-2 months, I hope we'll be touching at least each and every component of image processing. At least the basic program in image processing to be implemented in quantum environment. So in next 1 month, we will be closing it. After that, even for 5 of my students, out of 5, 4 will be working only in quantum image processing. They are also exploring in their style. I hope in next 3-4 months we'll come with very good content with us. So with this, I'll stop here and thank you for giving the opportunity. And if you have any doubts, you can ask now. Okay. And see, don't think this as a complicated subject. So better you convert everything into very simple terms. Make sure that you are getting the confidence. So I always believe in getting the confidence first. So nobody can learn the whole quantum, or I think how many of you know the whole C language? I don't think so. Even those who taught it for 20 times or even 30 times also can't give guarantee that he knows the whole C language. But he is managing everything perfectly. So in the same way, don't think that you need to learn the whole quantum computing in next 1 month or 1 year. Whichever is required to you, if you are managing comfortably, then we can enjoy anything in the life. Okay, thank you. Yeah, please. Yeah, I told you, we need to convert everything into that quantum environment. Actually, the one which I have shown now, it is known as NEQR representation. So we must convert the given classical image into this quantum representation, because quantum computer understands only quantum bit representation. Yeah, we must get it. I'm telling no, but obviously, as at the present, everybody is saying that there is going to be some noise. We must remove the noise and tell it. So for this, you remember only one thing. So 2 plus 3, whatever the computing device that you use, you must tell 5 only. Even how much fast you tell, how much quick you tell, and whatever the technology that you use, you should not tell even 5.00001. If you tell that, that is of no use to anyone, no. But as of now, people are telling that there is going to be some noise. Obviously, even actually it has to be maintained in some temperature. Even in spite of all that, still people are telling that we get noise, and there are some noise removal techniques. But you need to do everything. At the end, you must say 2 plus 3 is 5. You remember that. We must get the same result. Yeah, we are using Python only. Qiskit is one of the library in Python. Qiskit, Qiskit. It is one of the library in Python, and there is one simulator. Actually, You can do this programming in two styles. One is by using simulation and one is by using your real IBM environment. Because IBM is giving us free slot for accessing it and using it. Better my suggestion, first you do simulation, immediately you experience it. In Google you type IBM quantum environment, you can log in into that by using your existing Gmail ID, but they give half an hour free access for 1 month. But half an hour is very good amount of time. Then when you execute the same program in that IBM environment, which is considered as real-time implementation or getting the feeling of executing the program in the real quantum computer. Otherwise, first we generally do a simulation and this one. For simple program, you test both because it is there in my slides. I'll be sharing mostly that content also to your organizers here.
Sir, one question from online. What kind of problems does quantum computing solve rather than traditional methods?
Yeah, mainly people talk about that factorization problem. So in addition to that, the drug discovery, that and all there, but really we can't know how they can be used. But in factorization, it is clear cut. Because if you consider that 2048 bit number, so with your existing supercomputer also, it will take hundreds of years, and that too there is no guarantee. But in quantum computer, that you can do that. Generally, we discuss with our Grover's algorithm. But if there are another problems also given, generally people consider it as it will solve very complex problems. But for us, at least time being, the complex problem is factorizing a given number, that very large number.
It is my privilege to propose a session remarks for this highly informative and inspiring session. First and foremost, I would like to express our heartfelt gratitude to our distinguished resource person, Mr. S. Raju Garu, Associate Professor, MIT Varangal, for delivering such a valuable session on quantum computing and lateral quantum computing. Sir, your explanation made it highly advanced and emerging area like quantum computing much easier to understand. The practical examples, thoughtful discussion, clear explanation of fundamental concepts such as qubits, vectors, superposition, and the power of quantum computation made the session highly beneficial for all the participants. We especially appreciate the way you connected quantum computing with current and future research opportunities. Your session helped us understand how emerging areas such as image processing, computing, and interdisciplinary research can be integrated with quantum computing in the coming years. The comparison of classical computing limitations with the speed and potential of quantum computing was truly thought-provoking. This session not only improved our understanding but also created curiosity and motivation among the participants to explore this field further. On behalf of our institution, the FDP organizing committee, project members, and all the participants, I sincerely thank you, sir, for sharing your valuable time, knowledge, and experience with us. So it is our privilege and honor to felicitate our esteemed resource person, Professor U.S. Rajgaru, for sharing valuable insights and expertise with us today. And I request to give the Professor.
Don't leave the main.